Good morning, everyone. We'll continue today our topic. We started the capacitors and we looked into the types of capacitors and how to calculate the potential difference and the capacitance values for several types of geometries, including the cylindrical, which is the coaxial cable type, spherical one, and the parallel plate capacitor. In last lecture, we have seen that the current density basically is proportional to the drift velocity of the charges. The drift velocity is due to the electric field, and it is, as we can see here, the current density is proportional to the drift velocity, which means that the current density is also proportional to the electric field. Now, this proportionality constant that we introduced here is 1 over rho. Rho here is the resistivity. It's not the density, the same symbol, but it is different. Rho is the resistivity, and it's a signature for the material. Every material has its own resistivity. Resistivity does not change at all. It measures how easy or how hard the charges can go through that material, and it defines a normalized resistance, as we will see later on, with a length of 1 meter, a height of 1 meter, and a width of 1 meter as well. The SI unit for the resistivity is ohm meter. So, as I said, resistivity is unique for every material. Resistivity does not change at all. Basically, we have conductors that have very low resistivity. We have insulators that have very high resistivity because charges in conductors or in metals in general, they can move freely, not the case in the insulator, and that's why the resistivity in insulators is high. So if we are to compare a few materials here, we have the silver, for example, which has the best or the lowest resistivity at ambient temperature, and then come the gold, then come the copper, and then the gold. However, on the insulator part, we can see that we have materials that goes up to the 10 to the power 16, which is the quartz, fused quartz, and also other material, other insulators as well. So the ratio between the resistivity and resistivity between the metals or conductors and insulators is extremely high. So let's look at this example. Here we have an electric field that is of a magnitude 100 volt per meter or Newton per coulomb. It's the same. Is used to drive electrons in an aluminum wire and a glass wire. So we have two wires. One of them is conductor, and the other one is an insulator. Each of the cross-sectional area is one, so they have the same cross-sectional area. What current will be generated in each wire? Knowing that the resistivity for the aluminum is 2.75 10 to the power minus 8 ohm meter, and for the glass it is 7.5 10 to the power 13 ohm meter. So the first thing to start with is knowing that the current equals to the current density times the cross-sectional of that wire. So in this case, if I am to calculate now the current density, I know that the current density is the electric field divided by the resistivity. I know the electric field 100. I know the resistivity here. I'm doing it for the aluminum. I know the resistivity for the aluminum is 2.75 10 to the power minus 8. Then the current density for the in the aluminum case is 3.6364 10 to the power 9. This is current density per meter squared. So now the current would be this current density that I just found times the cross-sectional which is the area of the cross section here, which is 1 millimeter squared, and this is 10 to the power minus 6 meter squared, and the answer is 3.6364 10 to the power 3 ampere. So this is the current for the aluminum. For the glass, same cross section. I need to calculate now the current density, which is the electric field, the same electric field for both, 100 divided by the resistivity of the glass, which is here 7.5 10 to the power 13. Then I get the current density, multiply this current density by the cross section, the area of the cross section. Then I get the current for the glass, which is 1.33 10 to the power minus 18. Notice the difference in the current between the aluminum wire and the glass wire. It's in the range of more than 10 to the power 21 times. So what is the relationship between the resistance and the resistivity? The resistance is the resistivity times the length divided by cross section. Remember, we said that the resistivity is the normalized resistance. So, what does normalized mean? It is for a cube that has a height of 1 meter, length of 1 meter, and a width of 1 meter. So, it is normalized. In order to get the accurate resistance, I need to know the dimensions of the resistor that I am measuring the resistance for, which means I need to know the cross section and I need to know the length. So the resistance here is the resistivity times the length divided by the cross section. We know that the resistivity is ohm meter, then the unit for the resistance is only ohm, where L is the length of the specimen here, and A is the cross section of the specimen, and we know that the resistance relies on the resistivity of the material. We know that the resistivity is a signature of this material. The resistivity does not change. However, the resistance can change for the same material. How? By building different structures with different dimensions, the resistance will be different, but resistivity will never change. Resistance, however, will change based on the dimensions of that resistance that you are measuring. So it's a big difference. Resistance depends or relies on the geometry. Resistivity does not rely on the geometry. The resistivity does not change. Resistance varies based on the shape of the geometry. Now let's look at this question here. If we have an ohmic conductor, this is a conductor carrying a current. The cross-sectional area of the wire changes from one end. As you can see that this cross-section is increasing along the wire till it becomes this cross-section. Which of the following quantities vary along the wire? So we have to be, aware that this is, let's say, A1, this one cross section is A2, such that A2 is greater than A1, and the cross section along the wire itself is increasing. So which of the following quantities vary along the wire? Resistivity. We said resistivity does not change. Resistivity is always unique for every material. So resistivity does not change. What else? The current. The current does not change. The current is the same in the structure or in the conductor. The current does not change at all. Current is staying the same regardless of the variation that happens. We will always have one current. What about the current density? Well, current density is the current divided by the cross section. If my cross section here is increasing, then definitely the J is also going to increase along the along the wire. So J does increase. What else? Electric field. Does the electric field change along the that wire that has a cross section that is increasing? Well, based on the relationship that we have looked at earlier, where we said that the current density equals to the electric field divided by the resistivity. And here, the electric field is a function of the current density. So the electric field is rho J. If J is, in this case, J is decreasing, J is decreasing because the cross section is increasing. So J will be decreasing. We know that J equals to I divided by A. So J is the current, the cross section is increasing. Current is staying the same, then J is decreasing. If J is decreasing, then the electric field would be also decreasing, which means the electric field will vary along the wire, and in this case, it will be C and D. Now, if I have two wires that have the same length and I put them, beside each other's this way, what's going to happen to the total resistance? We know resistivity does not change. However, the resistance here it's going to change. How is it going to change? Well, I will call those two wires that are connected this way as in parallel. So in this case, if I start with those two wires that I talked about, that I put them side by side, connect them this way, such that they are connected in parallel. Every one of them has L and also have the cross section A. So what's going to happen now to my resistance? Now I know that this R parallel in this case equals to rho times L. They have the same length. Now this new resistance has the same length divided by the summation of those cross sections. So it will be A by A. So in this case, if I take the inverse, so 1 over R parallel equals to A plus A divided by rho L. And in this case, I can say 1 over R parallel equals to A over rho L plus A over rho L. And indeed, 1 over R parallel equals 2. If I am now to rewrite this one such that 1 over rho L over A plus 1 over rho L over A, and in this case 1 over R parallel equals to 1 over R plus 1 over R. If this one has a resistance of R and this one has a resistance of R, then in this case I can say that the parallel configuration, if I have two resistors in parallel, the equivalent resistance would be the inverse of the equivalent equals to the summation of the inverses of those two resistors. Now, what's going to happen if I have uh, those two wires connected in series? They have the same length. However, I connected them in series like this. What is their equivalent? So this is R and this is R. They have the same length and they have the same cross section. What would be the equivalent resistance in this case? So here I have R series equals to rho. Now I have here L plus L divided by A. So this is the total resistance. So here I have R series equals to rho L over A plus rho L over A, which means that R series equals to R plus R. What does this mean? This means if I have two resistors that are connected in series, the equivalent resistance would be the summation of those two resistors. If I have two resistors that are connected in parallel, the inverse of the equivalent equals to the summation of the inverses of those two resistors. Let's now introduce the DC circuits that will be using those components in for the analysis. In DC circuits, we're only dealing with currents that are travels in one direction. So charges are only traveling in one direction, and this is why we call it direct current. Sources like sources that are used in DC circuits are batteries, for example. There are voltage sources that can generate potential difference, and they also generate a current, a DC current, a current that flows in one direction. So if you have this battery that has a positive and a negative terminal and you connect it in a circuit, the current will always go from the positive toward the negative, and this is the convention that we have agreed upon for the current, that the current is always going from the positive terminal toward the negative terminal. They always deliver power or energy based on the direction of the current. They go from the positive toward the negative. Now, the components that we will be seeing in our DC circuits are the following. We have the batteries. The symbol for the battery, as you can see, are two lines. One of them is longer than the other one. The longer one is the positive. The shorter one is the negative. We have the resistor. The symbol for the resistor is this. We have light bulb off. We have light bulb that is on, and we have the conducting wires. Now, ideally, we will be using those wires, assuming that those wires are ideal, which means they have zero resistance. They don't have any resistance, those wires. So we'll be using ideal wires. We also have a switch. This is the switch at the open state. When the switch is open, as you can see, it is open like this, which basically means that the circuit is broken. I have no current. I have zero current going into an open switch. Now, if the switch is closed, then this switch is gonna act like an ideal wire, has zero resistance, and the current will now be able to flow in this wire. Let's look at a few examples here. We have a flashlight. This flashlight bulb has a 12 ohm resistance. So this flashlight bulb has a 12 ohm resistance, and it's connected to a battery that is generating 6 volt through a switch. Now, when the switch is closed here on the right case, it was open. Now the switch is closed, and now we're looking at this circuit. What is the electric potential at AB or at A and at B? what is the electric potential at A and at B. Because now the switch is closed, this is considered an ideal wire. An ideal wire, which means that the potential right here at the positive potential of the battery will show up here. So here I have 6, then this is going to be 6 volt, and I also have 0 at the other terminal of the battery, and this 0 is going to show up right here at the B. Why is this? Because of the ideal wires that I have connected the terminals of the battery to the light bulb. What is the current through the bulb? The current through the bulb is as simple as now using Ohm's law that you've used in high school before. Using Ohm's law, we know that in Ohm's law, the potential difference across a resistor equals to the value of the resistance times the current going into this resistance. So let's look at our light bulb here. We have a light bulb that has a 12 ohm resistance, and it has a potential difference across this light bulb of 6 volt, which means if I want to calculate the current, then now the current equals to the potential difference divided by the resistance, and in this case the current I would be 6 divided by 12, and this is zero point 0.5 ampere. What is the current through the battery? Well, since I have here uh, a closed circuit, I have a closed circuit here, and the current now is going from here all the way back, then definitely the same current that goes through the bulb would be the same current that goes through the battery, which is zero point 0.5 ampere. In which direction does the current travel? Well, we've already drew the current. We know that the current goes from the positive terminal of the battery and goes back to the negative terminal, which means that the current now is going clockwise. Now we've introduced the DC circuits and the sources that we will be dealing with and the component in our circuits. I can now talk about resistors from different types. They don't have to be ideal like we have seen earlier when we calculated the equivalent resistance. Now, any two resistors that are connected in series, and the definition of the series is both of them they are sharing one terminal here, and no other component are sharing this this joint here, and this basically guarantees that the same current is going to go through both of them. When they have the same current going through them, this means those two resistors are connected in series, and that's why the equivalent resistance for resistors that are connected in series is the summation of those resistors. So R equivalent in the case of the series is as simple as the summation, which is R1 plus R2 in this case. So this one is R1 and this one is R2, then R equivalent is R1 plus R2. Now, how can we derive this? We can derive this easily, or to prove this easily, I would say, by having two resistors. Those resistors are connected in series, as you can see, and then with a battery source here. Let's call this one VS, and this one is R1, R2, and we said that the current will go from the positive toward the negative, which means both of them are sharing the same current. VS, the voltage, equals to what? Equals to the current times the equivalent resistance, or here I have the voltage Vs will be the summation of the voltages V1 plus V2. So I have Vs equals to V1 plus V2, right? Vs is I times the R equivalent. This is Vs. However, V1 would be I or R1 times I, and V2 would be R2 times I as well. So if I take I outside, so I times R equivalent equals 2. If I take I outside, I have R1 plus R2. So if I compare now both sides of the equation, I can see that R equivalent is the summation of R1 and R2. Now, this is for the case of the resistors in series. What about the case of resistors that are being in parallel? In this case, let's take a circuit that has two resistors connected in parallel, again R1 and R2, and those are connected to a voltage source, which is a battery in this case. Let me call this one Vs. Those are ideal wiring, which means the potential here difference across the battery will be the same as the potential across R1 and across R2. So both of them will be Vs, right? So if I am now, this is the current, again, I. If I know now that this I will be splitting into I1 and also I2, then I know that this total I should be the summation of I1 plus I2. So what is I? I indeed is Vs divided by R equivalent. This is for the battery here. And I1 is indeed Vs as well, because this is also Vs for both of them. So Vs divided by R1, and the I2 is also Vs divided by R2. Remember, those two are electrically considered. This is one node, and it's the same as the potential here at the positive electrode. And this one is also considered 1 point, and they have the same potential here. So indeed, Vs is also across R1 and R2. So in this case, Vs is common, so I can cancel Vs, and then I end up with 1 over R equivalent equal to 1 over R1 plus 1 over R2, which means that the inverse of the equivalent resistance in parallel configuration equals to the summation of the inverses of those resistances in the circuit that are connected in parallel. So this is for the parallel configuration. The inverse of the equivalent is the summation of the inverses of the resistors. And this one is the series configuration where I have resistors in series. Then the total resistance or the equivalent resistance would be the summation of those resistances. Now let's look at this example. Here we have this circuit. We need to find the equivalent resistance of the following circuit. So what do we have here? I can see that this 3 ohm and this 5 ohm are connected in series, which means now I can simplify the circuit to the following. And I really suggest that whenever you do a simplification of a circuit, that you draw it again. Of course, you have to understand what does this mean here connected to that point. Basically, electrically doesn't mean anything. Those are all 1 point. So let me first redraw the circuit. Fixing this, it will look like the following. So this is the 3 and this is the 4, this is the 2, and then from here I have the 5, and then I have the 3. 3, 5, 2. So basically, this is this. Now I know that the 3 and 5 are in series, then I can now simplify this further. It will be like this: 4, 2, and now here this one will be 8. So I have 8, 2, and 4, 3. Then I have 4, 2, and 8 in parallel, which means that the R equivalent now would be 1 over R equivalent equals to 1 over 4 plus 1 over 2 plus 1 over 8. And then in this case, 1 over R equivalent equals to 7 over 8, and R equivalent would be 8 over 7 ohms. So this is the R equivalent for those three resistors. Now after I found this resistor, the total R total would be this R equivalent plus 3, and then R tot would be 3 plus 8 over 7, and the answer would be 4.14 ohms. Okay, so let's solve this question. In this question, we have the switch in the closed here in this circuit closed. So this is circuit number A. Circuit A has the switch closed. There is no current in R2. There is no current in R2. We know why. Why? Because this switch now that is closed is working as a short circuit for R2. It is in parallel with R2, which means it is shortened out. All current are going through this switch now. No current will be going in this direction. Why? Because it is shortened out by this closed switch. So there is no current in R2 because the current has an alternate zero resistance path through the switch, and this is what's happening here. There is current in R1. Yes, there is current in R1, and this current is measured with the ammeter at the bottom of the circuit. This is the ammeter that measures the current, which is in series. Impose does not impose anything on my circuit, so does not affect my circuit. It's an ideal current. Now it is the current is read by this ammeter. We don't know the reading. The question is the following: if the switch is opened, so what we know right now that this switch is closed, which means no current is going through this resistor R2. All the current is going through this R1, and the ammeter is reading something. Now, if the switch is opened, now the question comes. When I open the switch, there is current in R2 now. Switch is open now. There is no current going in here at all. Now the current is going to take this path, go all the way in R2 and then in R1 and continue, will be measured by the ammeter and then close the circuit. What happens to the reading on the ammeter when the switch is opened? So we know now the situation. We had a switch that is closed, shortening this R2, and there was a reading. Now I open the switch, and the question is asking me what's going to happen to this ammeter. Am I going to see the reading going up, or the reading going down, or the reading does not change? What's going to happen to this ammeter? Let's analyze the circuit. When we had this switch closed, I had this resistor completely outside the circuit. It's shortened out. The total resistance is defined only by R1. And this current has been read by the ammeter. Now let's look here what's going to happen to my current. When I open the switch, now the current is taking this path that has R2, which means now the R equivalent in this circuit now has increased, became R1 and R2. Here, here the R in this circuit was only R1. Here in circuit number 2 or B, R equivalent is R1 plus R2. So if I have the same battery, the same potential difference did not change, and I all of a sudden increase the resistance that this battery is sending a current through, what are you expecting to happen to the current? So the current here, I1, is V, or call this delta V, divided by R1. The current here, I2, is delta V, the same, divided by R1 plus R2. So which current is greater? So this current was shown here on the ammeter. Now after I open the switch, now this current is going to show here on this ammeter. So which one is the correct answer? Definitely the denominator here is greater, which means that I2 is less than I1, and the reading goes down. So we have an example here. Compare the resistance of 100 meter long wire made of copper that has a diameter of 1.024 millimeter width. Now this bulb, we know that the resistance of this bulb is 140 ohm. We need to compare the resistance of this 100 meter with 1.024 millimeter diameter copper wire with the resistance of 140 ohm for this 100-watt light bulb. So let's start first with the resistance. We know that the resistance equals to the resistivity times the length divided by the cross section of the geometry of the resistance. So here we have a wire of 100 meter. This means that the length here is 100 meter. We have the diameter as 1.024, which is the area here of the cross section, which is pi the diameter divided by 2, which is 0.512, 10 to the power minus 3 squared. If you do the calculation, you'll see that the resistance for this wire that is 100 meter long with a diameter of 1.024, almost 1 millimeter diameter, the resistance is 2.1 ohm. However, the resistance for the light bulb is 140 ohm. Now, if you want to calculate the potential, what is the potential difference across each for 1.5 ampere? So if we have the same current going through both of them, what is the potential difference? I know from Ohm's law that the potential difference equals to R times I. I have R here, 2.1 for the copper wire, and the current 1.5. And I also have the resistance for the light bulb, 140 ohm times 1.5. Then the potential difference for the wire is 3.15 volt. However, the potential difference across the light bulb is 210 volt. One more question here. We have the following circuit. As you can see, I have two resistors here, 10 ohm and 1000 ohm connected in parallel. Which statement is correct? One, The current in IAB equals to the current in BD plus the current in BC. The current IBD is this one IBD, and this one is IBC. The current in IBD is greater than the current in IBC, and the current in IBD is less than the current in IBC. So which ones are correct? Now remember here, IAB is the total current, and this total current is being split into two currents. So I have IAB equals to the summation of IBD plus IBC. So I'm done with this. So one is correct. IBD greater than IBC. Is IBD greater than IBC? Both of those two resistors, they have the same potential. So if I am to say that here, just taking this part from the circuit, I have here between them V, let me call this one dB. The potential difference here across those two resistors, 10 and 1000 ohm, is VB. So they have the same. However, here there is a current IBD, and here there is a current IBC. Which one is greater? Now let's put the equation here. I have VB, right? That is the same for both of them. So VB is, let's take the left resistor. VB is 10 times IBD, right? And I also have VB equals to what? Equals to 1000 times IBC. Now let's equate those two. Then I have 100 IBD equals 1000 IBC, right? 10, 10, and IBD is 100 times IBC. So IBD is greater than IBC, and 2 is correct, and 3 is wrong. So the answer is D, 1 and 2. Last question. We have a parallel plate capacitor that has a capacitance of 177 picofarad with a vacuum in between. So C naught is 177 picofarad with a vacuum in between. Suppose a dielectric now is inserted between the plates, while the potential difference, the voltage difference between the plates held at constant. So the voltage difference here did not change before and after. Select from the following list the changes that you expect to take place in comparison with the original vacuum gap. So the potential difference is the same. So if I put the famous equation, Q is C times delta V, right? So here I know if the potential difference delta V stays the same, and then I put this dielectric constant, then definitely the C node has increased. So the capacitance has increased. So if the capacitance increases, then definitely charges will increase, right? So what do I know? So I know that the capacitance increases. I know that the charges on each plate will increase as well. Now, half CV squared is the energy stored in the capacitor. So if V is constant and C increases, then definitely the energy will increase. The electric field is not going to change. Why? Because I know the electric field for such a component is sigma divided by epsilon. Epsilon has increased, right? But also sigma, the charges has increased with the same ratio, which means electric field stayed the same, and that's why the answer is A, E, and G.